Everybody. My name is Kevin Hao, and I'll be talking about Science Olympiad Vehicle Events in this video. So this video is not specifically tailored to this year's events, which are Battery Buggy in Division B and Mousetrap Vehicle in Division C. So this video is just going to be going to go over the broad principles of vehicle events for Science Olympiad, and hopefully these principles will be able to be applied to any of the vehicle events, and that way successive videos won't need to be created, and all the information will be covered in here. So things that are going to be different about this video than a lot of the ones that are available online is that I'm going to go into some very advanced topics while trying to remain practical. I want it to be things that you guys can use and not just theory, as well as explaining how to apply these principles to your vehicle design and the competition. So a little bit about me first. I competed for Boca Raton Community High School from 2014 to 2017 for 3 years. And I went to the national tournament in 2016 and 2017. I competed in a pretty wide variety of events, including the tech physics events, which were probably my main events. But I also did some other events like geologic mapping, dynamic planet, entomology, invasive species. I had a pretty good variety. And I now attend the University of Florida studying biomedical engineering with minors in biomechanics and chemistry. I founded University of Florida Science Olympiad. We hold a regional tournament each year now, as well as we will be hosting a state elementary tournament. Hopefully have some good turnout for that tournament, and just see how well it can be run, and the interest from the teams. I'm also involved with Florida Science Olympiad as an organization on the whole. I attend board meetings and help with logistics with the state tournament as well. And I do supervise at a variety of tournaments across the country each year. This year I will be going to MIT, Harvard, Princeton, nationals, and maybe a few more. So my experience comes from competing in these events. I kind of realized as a sophomore towards the end of my year that electric vehicle and robot arm were coming in, and we didn't really have anybody on the team that could take those events over. So I saw an opportunity to learn Arduino and AutoCAD and become fluent in these skills over the summer before these events rotated in, so that once they did, I'd be able to just dig right into them. Relevant accomplishments: I did place second at the national tournament for electric vehicle in both 2016 and 2017. And I have a few other placings listed there. So this is my 2016 device, which we did take second place at the national tournament in with my partner Mac Gerstel. So a few interesting things to note about this device. You can see the main chassis is all made of carbon fiber. We 3D printed out of PLA for the intersections that are shown there. You can see it's 3 rods that are running parallel on the front and rear that are making up the track. So the track is defined as the distance between the outermost part of the left wheel to the outermost part of the right wheel, which is basically the width of the device. And then you can also see the wheelbase, which is supposed to be the distance between the front and rear axle. And that's connected by these 5 carbon rods here. It's a little bit hard to see in this top photo, but if you look down over here, you can see how it's almost like a pyramid shape, just missing the top rod. The reason we went with this kind of weird design for the chassis was we wanted some flexibility in the frame to compensate for any imperfections in the track. And it worked out really nicely, and it was quite light, very strong, very flexible. You can see our axle was carbon fiber. It's this carbon fiber rod that was fitted into these ball bearings here. And we did use Bainbot wheels for all 4 wheels. You can see this laser pointer in the center here that was used for aiming, which has played a huge role in our success. The rotary encoder at the side here to keep track of axle rotations. And that's kind of how we figured out the distance we were at and controlled that with the device. We used 3 microcontrollers, 2 Arduino Unos, and 1 Nano. The 1 Nano was just to record the rotary encoder and just keep track of the rotations there. The encoder we used had a high output feel like it was like 12 or 14 bits of digital output, which is a lot of information to keep track of. So we really found the need to separate these functions to separate microcontrollers, just because we didn't have a processing speed on one. And if we try to just run everything on one, it would start to miss clicks and stuff, and then we wouldn't have the right distances, which is a huge problem. You can see another Arduino was used with an LCD screen. That's how we input the distance. So we didn't have to plug this into a computer at competition. All we had to do is turn on the device and then select the distance that we were aiming for on the LCD screen, and we would just hit select and let it run. We didn't need a computer at all, which made it a lot easier. No problems with supervisors just not wanting to see that. It took a little bit of work to make this setup, but I think in the end it made a huge difference and made testing a lot easier as well. We have a third Arduino that was used as the master communicator, so both the other two Arduinos were feeding information to it. So this one was like the master control center, and it also outputted signals to the ESC to control the brushless motor, as well as taking in information from the rotary encoder and the LCD screen and compiling that and processing that information. You can see the transmission we use on the rear here, a Traxxas transmission. I do not know a ton about the ratios that we used. My partner did a lot of the work with that, but it was quite useful, and we continued to use the same transmission the next year. We have a voltage regulator that you can see down here, and that was just feeding the motor a consistent voltage, as well as powering any other electronics that we needed at a certain voltage. I don't remember exactly what we were using it for. I think the motor was run just purely off the 7.2 nickel metal hybrid battery that we have under this steel block over here. And I think this voltage regulator was to ensure that when the voltage dropped, because the motor was pulling so much current, that the electronics on board wouldn't turn off. So it would boosted up the voltage if it was dropping, so that the Arduinos were getting fed a constant voltage, which was very important to make sure that they did not just turn on and off. We did have that problem a little bit. The steel brick here, so that was, we wanted some more weight over the rear axle just because we were accelerating so much, and we just needed more frictional force, so we just increased the normal force. In retrospect, it might have been better to get new wheels. We used these blue wheels, but they were not as soft as, say, the orange or the green ones, and I'll go into that a bit more later. So this was our 2017 vehicle. A lot of it has similar designs as the previous one. You can see the same transmission here. We use the same transmission, same motor, same ESC. That all stayed the same LCD screen. We did change the wheels. We went to the orange 0.4 inch width, 2 7/8 inch diameter Bainbot wheels that are the 40A Shore durometer rating. And we primarily switched to these wheels because we wanted something softer in the rear compared to the blue wheels that we had the previous year. But we also needed to keep them thinner too. We were very concerned about keeping the profile of the device very skinny, just because of the bonus that was implemented that year, which was to travel between two cans. Pretty much exactly the same as Battery Buggy this year. But we really wanted to try and maximize that bonus, and by trying to keep the vehicle as skinny as possible and reducing the track width, it was really helpful. Some other interesting things that you can see, we used the same laser, but we had it at an offset angle here. That was just for aiming purposes. I'll talk about that more a little bit later. The dowel, of course, is in the front. You can see the caliper that we use here for doing the steering. So we set up a linkage system, as you can see. So this caliper, we cut off part of the caliper here just to make sure it would fit in this smaller area. And we didn't really need the full length of the caliper. Obviously, very small increments of the caliper resulted in huge changes with the angle. And we really only varied it by a couple millimeters, I think, at the end. Yeah, it really wasn't too necessary to have a large movement there. We attached the main caliper portion here, this tooth here, to a 3D printed part. We epoxied that in, so that was very solid, very rigid. And then so this was our first linkage here, and then we had this arm here that connected this first linkage the arm composed the second linkage, and then the third linkage here. These, you can see the ball bearings there, so those were free to rotate. And this third linkage arm here was directly connected to the front axle. So that is how we controlled changing the angle that the front wheels started at. Because obviously we need to change the curve based on the distance. And I'll talk a little bit more about that later as well. We switched to a LiPo battery this year. I think we were having, the nickel metal hybrid batteries weren't as consistent as the LiPo batteries. So LiPo batteries will give you a constant output for a longer period of time, and then they'll like drastically start to decrease their output. Whereas nickel metal hybrid, they kind of slowly decrease over time. So we found the LiPo battery just a lot more consistent. And I'll talk about that a little bit more later too, why that was so important for us. You can see the same voltage regulator in here for our electronics. That didn't change from the previous vehicle. And the encoder, it was the same encoder, but now if you look at this profile picture over here, you can see how we use this belt. We use this belt system here to remove the encoder from the front axle and actually offset it towards the rear. If we had the encoder along the same axle, say just directly connected to that front axle, our vehicle width would be larger. We were looking for ways to reduce that, and using this belt system on our encoder really helped with that. It did introduce more friction, but in the end, just for electric vehicle itself, perhaps not other vehicle events, our motor was just so powerful. We were only using like 30 or 40% of its capacity, so we really weren't too worried about friction and all these other things. We could just turn up the motor. Our real main limiting factor was our frictional force that we were getting. That's really what limited our speed and our times. It wasn't really the motor. You can see the box we made over here to the side as a carrying case. So whenever we would travel, we're from Florida and we went to a lot of invitationals. So it was very important for us to be able to have a consistent way to travel with our device. So we built this box out of, I don't even remember what it was, these pieces of plywood or whatever. And it was very, very strong. We had a handle for it and everything. And so when we were traveling, we'd put the device inside of it and then foam it and pad it and make sure the device wasn't moving inside of the box. And we just put this box inside of a suitcase and check it in on the airline just like that. And we never really had a problem with anything breaking. It was very strong. A secondary purpose that this box served was once we were impounding our device, we could put the device back inside this box and lock it up. So no other teams would see our device, get any ideas. As much as Science Olympiad is about collaboration, when you're looking at the national tournament and you really want to be able to have a strong finish, it is important to conceal any ideas that you have, just so they're not freely seen. I know a lot of teams will just use those clear bins, and I've seen other teams looking inside of them, just checking out other people's vehicles, looking for ideas. And this can cost you that top spot at nationals. So I would also be careful about that. Not only that, but more importantly, people are just walking around sometimes by the impound. Other teams might be putting their devices down, and if they accidentally step on your device, there's no way to keep track of that. I mean, you're done for that competition if they broke it. So having it in a locked box really helped with that. We weren't worried about somebody accidentally destroying our device. We knew it was going to be safe at impound. You can see this this computer-generated rendition of our device. So not so much for 2016, but in 2017, we found it very helpful to have all of our devices, including robot arm and hovercraft. We designed all of these in CAD first before we started creating them, just so we could catch any problems along the way early. And we wouldn't be resulting towards printing pieces again, or just running into these huge problems that would give us like a setback. We would be able to find these problems first in our renditions and be like, oh, well, we can fix that now before we even create it and have a physical copy of this. So that was certainly very helpful. Another thing that you can't really see in the device, well, you can see this threaded rod running through here. It's between these two carbon fiber rods. So this threaded rod, that's kind of how we initially adjusted our chassis. So it's very important to have a very straight chassis. And we used that threaded rod to make sure that each side was even with each other when we were constructing it, because those carbon rods were very hard to adjust. Like this frame, you cannot adjust this frame. It's very, very strong, very sturdy. Like even with a hammer, like you're risking breaking a lot of stuff, and you might not even, regardless of how much you hammer it, might not even adjust it. So having the threaded rods helped us initially set the dimensions of the frame, and then once we had it set, then we epoxied that. And that is actually something that we saw on, I believe it was LASA's device at Golden Gate, and I'll give them credit for that. And that's something we tried to implement ourselves after seeing it. So the first topic that I'm going to talk about are the axles and wheels. So how are you supposed to pick what to use for your axles and your wheels? I mean, there's so many options. And I would say for axles, the most common you'll see are the threaded rods, probably stainless steel. Those are just very available at Home Depot, Lowe's, wherever you're going to go for hardware. But so it kind of depends. If you can use electronics, it doesn't really matter so much, because the threaded rods were really just used for wing nut systems, and that is their primary use. But if you don't need a wing nut system like we didn't, the carbon fiber rods are actually quite good. So they have a very low rotational inertia. They're very light, very strong, very malleable. So you can use them for other things if you need to modify them or for whatever reason. And they do fit the ball bearings, those normal, I think they're like 22 millimeter diameter ball bearings. They fit them perfectly, like the standard bearings, which makes it very easy when you're trying to figure out how to construct everything. As for wheels, you can see this durometer rating I pulled up here. So with the Bainbot wheels, they're given as 30A, 40A, and 50A, where the 30A is the green ones pictured below here, 40A are the orange ones, and 50A are the blue ones. And what that means is how soft they are. So the 30A wheels, like they're pretty soft. I mean, if you push against them, you can definitely feel a difference between the 30A and then even the 40A. So that the advantage with the softer wheels comes when you have a lighter device and you need more grip. If you're going to have a smaller normal force, just because the mass of the device is smaller, you're going to need a higher frictional coefficient to compensate for that. But once your device starts getting heavier, you don't want, if you all of a sudden brake suddenly with say the 30A wheels, you're gonna start really degrading them very fast, and they're gonna lose their quality, and you're gonna see these little rubber pieces falling off of them. So that means you might want to switch to a less soft wheel, which would be the 40A or the 50A. So it kind of depends on the mass, I would say. I felt that the 40A was a good in between, but if you're doing something like Scrambler or Battery Buggy, where the device is very light, you might be best off with those 30A wheels, the green ones. So a little note on axles and wheels. I really recommend buying your wheels unless you have a laser cutter. Even if you 3D print your wheels, it's so hard to attach them properly to get it perfectly perpendicular. They can deform, like if you leave it in your car and it's hot outside. I've seen 3D printed parts like just completely melt and deform. And if it even just deforms slightly where you can't even notice it, it might have an impact on your performance. Additionally, once you 3D print it or laser cut it, say out of acrylic or PLA, I mean, what are you going to do next? Like, you're just going to put a rubber band over it or a balloon? I mean, it's just not as good as the Bainbot wheels that they have available. So I'd really recommend buying your wheels unless you really need to conserve on weight. And if you need to conserve on weight, there are ways you can drill out the Bainbot wheels. You just take a drill and just start punching holes into them. I know people have done that to reduce the rotational inertia, and it really does help. And you should be able, if you do it properly, you can maintain the structural integrity of them pretty well. You just have to watch out and have a plan for that. As far as the diameter of wheels that you want, so it really depends on your motor RPM, your transmission, your gearbox, the ratios that are going to affect there. So there's a lot of variables for that. So trying to figure out exactly what diameter you want, it's almost you kind of have to pick one. So you can say, okay, I want this diameter, so now I'm going to find a motor and a transmission that are going to match this and set this up right. Or you can say, well, this motor runs perfectly, or it runs most efficiently at this RPM, so I'm going to pick wheels that optimize that. So there's a couple ways to approach that. I will say one thing, that wide wheels do experience less drift, and the vehicle will travel straighter. So the larger diameter wheels will be better with drifting than the smaller ones, just because there's fewer rotations that are being completed. As far as motor selection, I don't want to get too far into this because this is kind of strictly for battery buggy and electric vehicle. And so the graph I have on the right there shows RPM and the power. So it kind of shows you what RPM this a motor might run the most efficiently at. I don't know exactly how many motors will come with this kind of thing, especially the hobby motors. I don't know if this is available to a lot of hobby motors or it's just very few, but that could be useful depending on what you're looking at. So kV ratings, those are very common when you're looking at brushless motors. I'm not so sure about brushed motors though, but it's kind of just telling you the number of revolutions per minute that a motor will turn at 1 volt, but that's with no load applied. So you have to be careful when you're looking at RPMs because those are usually given at no load. They're not used. They don't use a dynamometer, which kind of measures RPM and efficiency with varying resistance. That's not really given. So just taking a raw RPM, if you find a motor online that says 4,000 RPM, it doesn't really mean that it's going to be 4,000 RPM once you're running it and it's attached to a gearbox and a motor and wheels and everything. It's not going to run at that same RPM anymore. It's going to be lower. So you can't just take those RPMs and do your calculations based on that. You kind of have to figure out, okay, well, what RPM would it run with a load on it? And that is not something most manufacturers will give you. So it might be something you have to determine on your own. So I think that's all I have to say about that. Now with the chassis, so there's a lot of options you can go for. Some people will prefer carbon fiber, some people will use wood, acrylics, metal. I really don't think it matters that much in my opinion, unless you're trying to conserve weight. So with electric vehicle, we were not concerned about conserving weight at all, but with battery buggy or mousetrap vehicle, you are certainly concerned about cutting down your weight just because you don't have as much power coming from a motor or anything. So for me, we used carbon fiber and 3D printed parts solely because we just had that available to us. It wasn't that we were just looking at that and like, well, this is the best material, we're going to use this. It was really just that we were most comfortable with that. I know a lot of very successful people that use stainless steel or that used different metals, use wood, acrylic. So you really don't need to use carbon fiber for any reason. It is easy to work with though. My only tools that I really used were a mallet, pictured to the top left over here, and a Dremel. I really didn't use that many other tools besides those. I was able to build the entire frame just by those and the parts I printed and the carbon fiber. Whereas if you were to go with aluminum or some sort of metal, you're going to need a lathe or a mill. And I do have a friend, David Yang, who placed first in an electric vehicle in 2017 from Mira Loma. He did use a lot of metal, a lot of aluminum, but he had access to a lot of different equipment that is pictured here. So if you don't have access to that equipment, it might not be a good way to go for you. Alternatively, if you have a laser cutter, you can do acrylic. I know there have been a lot of very successful people using acrylic. It's a little bit more tricky, perhaps a bit more fragile, but it can be just as effective. These are the glues I use. I preferred the purple glue, which is kind of an intermediate between the blue super runny glue and the pink thick glue. And then the accelerator was quite helpful. I know these glues are very commonly used in boss events. I also use this clear epoxy. So if I'm just trying to, once I have my frame set and it's like perfect and I don't want it to shift by any chance, or I just want to make sure that there's no chance of anything like moving around or anything, I'll usually coat a lot of the intersections with epoxy. And this also goes for if a 3D printed part like breaks on me, say a couple days before a competition and I don't have time to reprint it, I will most likely just epoxy it with that clear epoxy. That clear epoxy is very good. It's so much better than glue. I would definitely recommend using epoxy when you can instead of glue. It's a lot more permanent. And then pictured below here, the steel stick. So this is, I usually use this for when I'm trying to like fix a metal or something or attach some sort of metal piece to something. The steel stick is very, very strong, but it is carcinogenic, so I would definitely recommend putting on those latex gloves when you're using it. And there's not too many times where you'd find a huge need to use the steel stick, but if you do, this is a good option. So first, a lot of people are always wondering, well, what dimensions do I make my device? And in my experience, I would say maximize both. So you want to maximize both the track, which is the distance between the wheels on a given axis, as well as the wheelbase, which is the distance between the front and rear axle. So it's maximizing these is important because it reduces the deviation your vehicle will see given an imperfect aiming. So say you aim 1 degree off from this exactly straight trajectory, you're going to see a larger deviation with a device that has a smaller track and a smaller wheelbase than you'll see with a larger track and larger wheelbase. So it's essentially reducing your error, which is quite helpful because we can't aim perfectly, and being able to reduce that error in any way we can is going to be helpful with your score. And so some things you can see from this is, well, you can kind of base this off of what they do in professional racing. So I showed a drag car here, and you can see just how long it is, and that is really just showing, it's reinforcing the idea that maximizing that wheelbase is important because drag cars they're meant for speed, and obviously they have thought about these questions a lot more than we have. I mean, this is their main profession and job. So taking tips from the actual professional industries is always a good idea. So another interesting solution that's out there is this Traxxas Funny Car. So I actually saw a mentor using this at MIT, and it's like a model drag car, but it has a lot of the components that worked for Science Olympiad, and they performed quite well. The wheels and the front and just everything about it. The only problem is the steering and the customizability. So it's not quite the perfect solution when you're looking at being able to modify it for Science Olympiad purposes. But it was interesting to see how good you could go just modeling off of a real drag car, because they performed very, very well at that invitational. So some more examples. You can see this one on the left here is all acrylic, so it looks like it was laser cut. They assembled it, so this is certainly an option. These are from 2008 and 2009, where speed wasn't such an important thing. It was more like they were giving you a time. But you can see with this one, I believe this was Miraloma's device. You can see a scope that they were using for aiming, a belt here. And this far right one, they used a microcontroller to achieve the correct timing and everything. So you do have a lot of options. You don't have to go crazy with the carbon fiber and stuff. There's a lot of different ways you can build your device and have a lot of success. So I'm just going to go through a few of my friends' devices. So I collaborated with a few people, and one of them includes Nestor. So he's posted a few videos online about his device, and I'll talk about it a little bit just because he didn't quite make a video explaining it. So he used this caliper here. The Mitutoyo calipers are very, very well known, very good calipers, but they're quite expensive. So he attached the caliper to the axle using this kind of pillow block, and then from there he relied on the play inside of the bearing to be able to adjust it. So moving that caliper adjusted the angle that the axle was at, and that resulted in different changes in the steering. Then you can see he's got his encoder up here, and you can see that the encoder, it's a bevel gear attached to this that's interacting with this linear gear on the axle. So you can see that for the gears to properly mesh, the axle must have been moving very small amounts, and that is very true. He did not move that very a large distance, just small enough angles to achieve the correct steering path. You can see he uses this motor controller shield on his Arduino Uno, a nickel metal battery, and a laser pointer here for aiming. Up front, he has his motor geared up to the axle this way. And below that, I believe this was Montgomery's device, where they try to imitate Nestor's design, but with 3D printed parts instead of aluminum. And I believe they had pretty good success with this too. So this was a very good design if you just needed some sort of device to do well. You can really see how derivative this device was. I believe he sent them the plans for it at that point. This was David Yang's device from Miraloma, and me and him did collaborate a lot throughout the season, not just with EV, but with Robot Arm as well. But he went with the aluminum. He had access to milling stuff. So you can see with this top picture here, you can see his encoder, which is belted to the axle, similar to what we did. And that was just to be able to move the encoder away from that front axle and be able to reduce the width. You can see, so the way he was adjusting his steering was he had this, instead of having a fixed caliper, well, he had a fixed caliper as well, but I think initially he was playing around with this, but later shifted. If you look at these pictures below, he's got this fixed caliper where he drilled holes into the caliper and to attach it to the bearings here. And he had a similar linkage system, but it was a little different, where the caliper was free to rotate as well. So not only was the linkage moving, but the caliper was moving as well. It wasn't fixed completely. So I think he took away one linkage, and while we had an extra linkage. You can see the carbon fiber frame down here with machined aluminum parts connecting it. And let's see, he used a similar transmission, different motor, but quite similar as well. You can see the way he attached the transmission to the axle, to the wheel. I believe he machined components out of aluminum for that, whereas we 3D printed them. And you can see the final device here. He kind of built a box for all the electronics just to keep it neater. And I believe this was at Nationals where the device finished. And you can see the laser pointer here that he used, which is angled as well, similar to what we did. This is Surya's device. He placed first at SoCal. We had just kept in contact for a bit, and I thought it'd be interesting to show his device because it takes a very different approach than the ones I've shown you. Similar caliper method, and I don't think I completely understood his linkage system. It's quite different than what we did and that I've seen. But it's similar in that he cut off the caliper, and the caliper was completely fixed here. The caliper was not moving itself and rotating like David's device, but just the one side of it was attached to this linkage system to change the angles that way. And he used 3D printed parts and carbon fiber throughout most of it. See, a similar brushed motor setup. He looks like he had some sort of other transmission going on back here. Looks like it's more direct from the motor to the axle, just based on what I'm seeing. And he used a similar 40A wheels. Those wheels are very good for electric vehicle that year. This was Thomas Devlin's device from Harriton. They placed third at Nationals. So they took a very different approach here, using the 30A wheels and this very complex laser system that I have yet to completely understand. But from what I understood was that they're adjusting their axle with they have like this internal spring system. And they were able to adjust this just by opening up this area here. I think they had a nut here that they were able to turn, and they adjusted it this way. And then in addition to the actual aiming, and they had this huge piece here. So they had this dual laser system on the device, and as you can see, they have this belt system attaching the motor to the axle, so they didn't have to have any other transmission or anything there. They just used this belt. Similar Arduino microcontroller. I would assume there's an encoder in here somewhere. Looking for it. Yeah, I'm not sure. I don't quite see it. But I believe they did use an encoder of some sort somewhere. And this device had a lot of success. I was not in contact with Thomas a huge amount, so I can't speak to exactly how their progress went and if they ran into any problems with this design. But it looks like it went pretty well for them. This is Marcus Williams' device, which placed fourth at Nationals. And he was really just going for that bonus, as you can see. I mean, he managed to keep this device extremely skinny and quite simplistic compared to some of the ones I've shown so far. So he used a similar steering design as Nestor. You can see this caliper that's fixed here, attached to the axle. And then he kept the encoder at the front. Oh no, actually I believe this is the rear. Yeah, this is the rear. So the encoder to the rear with the bevel gears to allow that to read it. He had this DC motor here, just a simple brush motor with his large gear that he 3D printed. And I believe he did have problems with that gear like little teeth on it snapped off. So I'd be very careful about 3D printing gears. Perhaps just print an extra spare one just in case something goes wrong. I mean, he used a similar microcontroller and system as Nestor did, and he managed to keep this very skinny, and he was getting very good results before nationals. He had very, very good bonus scores, and I believe he posted a video somewhere online as well. So if you're really looking to get these really thin devices, this might be a good example to look at. All right, so I'm going to talk about weight distribution a little bit. So obviously this is a very important aspect of the device design. So as you can see, I'm going to start with the bottom here. So I was part of an SAE team. So it's a SAE, it's a racing organization for college students. And there's Formula SAE, which is used with typically motorcycle motors, motorcycle engines rather. And there's also electric SAE, which is typically with electric motors. So the University of Florida had a Formula SAE team, and I gained some experience through that. I didn't stick with that too long, really because I kind of realized my passion was more in the biomedical sciences rather than the mechanical sciences. But I did learn a lot about how they do weight distribution. So they basically put these let's just call them scales, underneath each of the wheels, and they can measure how much force is being applied to each scale. So they can kind of measure the weight distribution that is being applied to each wheel with these scales. And so there's advantages and disadvantages to having differences in your weight distribution. So more weight on the rear end can give you much better traction when you're accelerating. But having a larger weight on the front end will make it more accurate in your turns, because you'll have a larger frictional force on those front wheels when you're turning, and it'll reduce any kind of slip. And so you can see to the right of this image, it first shows static, where the front wheels each have 450 kilograms as measured by a scale. The rear wheels have 300 kilograms each. And as you can see, so then it talks about what it looks like during braking. So the apparent weight begins to look like 600 kilograms on each of the front wheels, and then 150 on the rear. And that's just because the inertia, it's all shifting the apparent weight of the vehicle onto those front wheels. So you're getting a lot of traction on those rear wheels, and you're losing a lot of traction on those. You're getting a lot of traction on those front wheels. And you're losing a lot of it on your rear wheels. So this is one of the reasons that a lot of cars, they will have their the primary brakes on the front, and the motor may be situated on the back. So say with a drag car, you're going to want that the wheels that are having the largest applied force on the rear, because the apparent weight is going to shift to the rear when you accelerate. So it'll almost look as if the rear has more weight on it, and you'll get a larger normal force, which will increase your how fast you can accelerate. The third picture shows in a right turn, you can see, so if you're turning to the right, you can see how it looks like it's shifting more pressure towards the left wheels. You can see the little black marks there. You can see it has more area on these left wheels than these right ones. So vehicle design, talking about steering, so there's obviously different ways to do steering. I think the caliper method has become one of the most popular in recent times. But that's probably primarily just because we've had these actual bonuses, and versus in past years when we didn't have a bonus. Obviously you didn't need to purposefully turn your device, but having a way to control your chassis and the way your vehicle runs, whether it be slightly left, slightly right, or trying to get it perfectly dead on, it's very important to have that. And as you can see, my 2016 device, we had this system of, it's just strings and then zip ties. We were able to slightly tighten those zip ties and then bias the frame, because the carbon fiber was slightly flexible. So we were able to ensure that our device was traveling straight just by adjusting those little zip ties. And that had a huge impact on our performance and how we were able to actually achieve such good scores. One of the biggest things is that no matter how perfect you think your chassis is, it's never going to be perfectly straight. It's just so hard to get those tolerances perfect. Different temperatures can impact the expansion of materials. There's just so many little variables. Say you're traveling and there's a little shift in your device. You might not even notice it, but then you try to run your device and it's all of a sudden turning one direction. So just building in a system to adjust your steering is very crucial, and it's gonna have a large payoff. You're not gonna have those frustrations of, oh, well, I know my vehicle turns slightly to the left, so I'm just gonna aim it slightly to the right, and hopefully it ends up dead on. You know, like that. It's just not a good system having trying to rely on that and trying to just compensate for it when you can just build in a way to actually fix it. There's different types of steering systems. I would say I showed images of the Ackerman steering just because that is I would say it is the best steering system that you can implement just due to the geometry, and it's not too complicated either. I built an Ackerman steering system, as you can see below here. This device didn't quite work out. This was towards the beginning of the 2017 season, where I had a servo at the front, hopefully to steer the device. So I was going to go straight and then turn right, go through the cans, and then come back to the center line and then go straight since then. But that was just so hard to control. I should have looked into accelerometers and stuff, but honestly, I kind of gave up and just realized that fixed curve was going to be a lot easier to control. And I do know one team that actually successfully did implement this, being able to turn, but I think they had some problems at nationals and they weren't able to. I believe it was Acton Boxborough, but they didn't end up pulling it off. It's very, very difficult. I would really recommend the fixed curve whenever you have a curved scenario. You can see this Ackerman steering. You can do this fixed curve or have a servo there for that. And so it's a little bit more complicated. It might not be completely necessary, but it's going to minimize any slip problems that we'll talk about later. Okay, so chassis torsion. This is not something many people think about, but it is actually quite important in the racing industry. So you can see with this bottom picture, you have your chassis here, and they have this beam. And then they apply a force to it, and they can see how much twist there is in the chassis due to this force. You can kind of measure the torsional rigidity is what they call it. So chassis torsion is important because you want to maintain good contact with all four of your wheels on the track, and if your device is too stiff, and say there's like a little imperfection in the floor, which of course there always are. You're going to lose contact, and that could impact a lot of different things. I remember at MIT electric vehicle, the floor was nowhere near perfect, and I saw a couple of cars with suspension, and that really helped them. But I did not have anything like that, and I think our vehicle paid for it during that. Just on the track, we saw a little bounce in it on the video that we took. So trying to keep that in mind is actually quite important. And as you can see, like with this carbon fiber frame that we implemented, it actually took care of a lot of the torsional parts. It was able to just twist based on the road just slightly and compensate for any imperfections. Whereas if you had just used like a piece of plywood as your entire frame, it wouldn't be able to do that unless you had some sort of suspension built in. And suspension can be quite tricky to implement properly, and it can give you a lot more problems in other areas, although it is something I do wish I had looked into. I think over here, so you can see this free rotation. This was where the caliper was getting attached. You can see in this CAD model, and it was free to rotate inside of this part, so that helped with the torsion as well, in that the front could actually slightly rotate, not just like turning the axle angle, but also just rotating it so that the wheels can maintain different contacts depending on if it was as the angle increased or decreased. It's kind of difficult to explain, to be honest. And I don't really know exactly how important that was, but I think it seemed like it was helping the device, so I just thought I would mention that. All right, so the next subject I'm going to talk about is aerodynamics. So this is something that's not too commonly talked about in Science Olympiad, but I felt it was worth mentioning. So in the first picture, you can kind of see this is a Formula SAE car, and below is an F1 car. So F1 cars travel at much higher speeds throughout the race compared to Formula cars, which have more maneuvering and acceleration kind of challenges they have to face. So you can kind of see the differences in the aerodynamics, where the Formula car has more pronounced aerodynamics, whereas the F1 car has much more subtle aerodynamics. And this has to do with you do increase drag as you increase your aerodynamics, so at higher speeds drag becomes more of an issue. So below we're looking at how the differences between aircraft and Formula cars and how they use aerodynamics. So aircraft use it to generate lift, which is an upward force, while Formula cars use aerodynamics to create a downwards force called downforce. And you can kind of see what it kind of looks like as a computational fluid model below here. And the aerodynamics are being used to pull the vehicle down towards the ground to generate more force and larger normal force, in addition to just gravity, to increase the frictional force being applied on these tires. That assists in cornering, makes cornering better, handling, as well as acceleration. You can kind of see the differences that are shown here with the airfoil between a race car and an airplane, and how they generate different forces, and the contributions of each of the components with a typical F1 car. So the real question becomes, does this even matter? I mean, nobody really talks about aerodynamics when they're talking about Science Olympiad Vehicle Events. And the answer to that is almost certainly not. They very rarely matter. And as a little demonstration, cars are typically said to have significant aerodynamics at 60 miles per hour. And bicyclists claim that 22 miles per hour is when they start to see the contributions of aerodynamics. So using these two different calculations, if we're talking about 22 miles per hour as the benchmark, you can kind of see that your time, your half a meter to 8.5 meter time needs to be about 1.73 seconds before it'll actually become influential. Whereas if we're talking about a car, it looks to be more about 0.64 seconds. And so with to compare to that, Troy's EV is one of the fastest times I've ever heard of. It was between 1.1 and 1.2 seconds. So you can kind of see how aerodynamics might have played a pretty pivotal role. If they were to try and play around with that, they might have actually been able to increase that time and see more pronounced changes, perhaps even with their braking and acceleration. Another topic that I find important to talk about is oversteer and understeer. So oversteer is essentially when you're steering too much. So you can kind of see with this car, the intended path of travel is along this direction here, this arc. But with oversteer, it's steering too much, so it's cornering even tighter. Understeer is just essentially the opposite, so this is your intended travel. And understeer, you're basically steering not enough. So you can kind of see how the curve is much wider, the radius here. So there are several implications of this. A lot of it is slip angle, we can see with the tires here. But I think the thing that most people are most interested in is how do you correct for that? And so here are some ways that you can correct for this. And a lot of it, it's more applicable to real cars. I mean, talking about springs, suspensions, camber with the wheels. We typically don't even talk about camber. It's a very complex topic and perhaps not even relevant. But something that we can look at is applying more downforce to the front or rear, as well as changing tire width, and perhaps changing the weight distribution here. So you can add more weight to the rear to correct for understeer. And there's similar things with the with oversteer that you can do. And this table has it talks about weight distribution. You can move it more forward or rearward. So if you're experiencing problems with oversteer and understeer, I would highly encourage you to play around with some of these ways that you might be able to correct for it. And so one of the things, especially with this year, with all the curving Once you travel in an arc, things do change drastically compared to just going straight. And so some of the reasons why you might be getting an inconsistent trajectory, and you might be kind of flustered about why you're not getting the same curve every time, is if your speed is changing. So something I found with using nickel metal hybrid batteries in 2017 when we had the curve with EV was that if I recorded a time that was lower than the previous run, so say this run, like the car went faster, it tended to oversteer. So I would see it, actually no, yeah, so it would typically tend to understeer, so it would have a larger radius, larger arc that it would travel in. And then it would displace the target to the vehicle to the right of the target. And then so that would change as because the battery was being drained over time after each run. So you would start to see these differences. So you keep trying to recalibrate your caliper or the steering, but like that wasn't even the problem. The real problem was the speed was changing. So that's something to look out for. That was due to understeer in that scenario. Steering calibration could be changing. Of course, that's a reason why the trajectory might not be consistent if there's a problem with your steering system and it's not rigid enough. And then also, so a big one was friction changing. So what we found was that we would clean our tires with, it was called belt conditioner, and it would essentially kind of like break down the surface of the wheels and make them softer. And it made them a lot more grippy, and you would think that'd be a good thing. It helped in acceleration and everything. But we tended to see strong oversteer. So the vehicle would tend to end up, the radius would be smaller that it was curving in, and it would end up to the left of the target point. And so say like the first run, we would see immediately after applying the belt conditioner and cleaning the floor, we would see it end up 13 centimeters to the left of the target. And then we'd run it again, exactly, we didn't change anything. We didn't apply belt conditioner a second time because the wheels were sort of kind of grippy. And we would run it exactly the same again, the same conditions, and we would see it end up maybe 1 centimeter to the left compared to 13. So it would just shift like 10 to 12 centimeters just due to changing the friction coefficients of those wheels. So they had huge impacts when you're going at those high speeds. So that could easily be another reason. And then from there on, we stopped using belt conditioner to clean our wheels. We went back to water just because we didn't want to see such inconsistency. So even though it was getting better acceleration and stuff, we wanted to make sure that whatever results and data we were collecting was consistent, and we'd be able to repeat this at tournaments. So watching out for, I would say, the speed. That these three things that are listed here are huge factors when if you're having problems with your trajectory. These are things that you should look at. So testing and data, of course there's different ways to do this. You can just collect a bunch of data and make graphs and just kind of try and guess on the graph what you need, which could work. Or you can create a regression and get an equation out of it so you can actually plug in numbers and have a real value for when you're trying to predict and adjust at tournaments. So you can just do a linear regression. So kind of what we did for 2017 that kind of demonstrates this is we collected data for the wheel, so the caliper angle, which is essentially the axle angle. We collected data for what angle we were aiming the vehicle at initially, because we would offset it. And then the distance, so those were like 3 variables, and we just kind of collected data for that at 9 meters, 9.5 meters, 10 meters, 10.5 meters, 11, 11.5, and 12, so every half a meter. And then we would just use a weighted linear regression to interpolate between the points. To say we want to hit 9.3, we would use the data from 9 and 9.5 and just like a linear interpolation to get the data that we want to use and the measurements that we wanted to use on our device. It actually worked very, very well. You would almost think that it wouldn't just be a linear relationship, but I think just because it was such a small change, interpolating it just linearly worked quite well. So that's one option. Another option is to use Eureka formulas, where you can just give it a bunch of data, and then you can have a function of however many variables you want, and it'll generate these equations. And you can just save these equations in your calculator, preferably as CXCAS. These ones have that function. I'm not sure about the 84s and stuff. They might too. I'm less well versed in those. But you can just save these equations, and then on tournament day, you just kind of input, say, the distance that you need to go at. Say it's 9.3 meters, and you can just say function of 9.3, and it'll just plug it into this equation for you, and it can spit out an answer. So this is another way to do it. I think we found that it wasn't necessary for 2017 and the curving, so I think linear interpolation might be enough. But we did use this program for air trajectory a lot, and we had really good results with that. So a couple more things I just wanted to mention before we end this video. So first, a packing list can be very, very helpful. There are going to be things that you need to repair your device if it breaks somehow in transit, or you just want to think of all these like crazy scenarios where something goes wrong and you're going to need to fix it. And if you don't have that thing to fix it, I mean, you're going to be in trouble. So I always had a packing list for nationals, less so for other tournaments, just because I had other concerns on my mind. But for nationals, I definitely made packing lists, and I basically just went through it and checked it off while I was packing, just to make sure I would have everything. And I think that is something very useful to do, just to make sure that nothing can go wrong. And of course, Murphy's Law, what can go wrong will go wrong. And of course, it'll be at tournament day. And that's just kind of how it works. I mean, you're stressed out. There's so many things on your mind. You're not thinking clearly. A lot of people, and this is something I recommend that I never did myself, but I really do think it's a good idea, is to have a run checklist. So say you need to calibrate your device, like you need to aim it, you need to plug in the, say you need to set your wing nut or whatever. There's like a bunch of things you have to do before each run, that if you like forget one thing, you'd have big problems. And it's almost a good idea to just have this checklist that you go through every time you set up for a run, just because you're going to forget things on tournament day. And I've certainly seen people just in their flustered panic and hurry just forget to set like something small, and then their run doesn't work and they don't do well at the tournament. This was especially important for air trajectory. I saw some teams, some really good teams, that had lists that they went through while they were setting up their device and calibrating it for each shot, and it was very, very helpful, because that is something that I ran into and had a problem with at air trajectory. Post-travel testing is very important, so don't just assume that, oh, well, I tested my vehicle at home, I packed it up, send it through an airplane or on a bus or on a car or whatever, and then you're going to get to the tournament venue and it's going to work just fine. I would definitely, once you get to the tournament site, go find somewhere where you can run that device, either the night before, or even better if you can do it the morning of. You can wake up a few hours before impound and like make sure your device is still running properly. You do not want to have some sort of steering issue. I've definitely had that happen to me. You want to make sure everything's calibrated properly, everything's running properly. I mean, changes in temperature, humidity, just problems in travel. If something gets bumped or something, those can all cause problems with your device, and it's important to make sure it's still working properly after travel. And with runs, I would highly recommend cleaning the floor and cleaning the wheels. Just changes in friction can have such a huge impact on your device, and you really want to make sure you minimize any problems with that. So I know a lot of teams carry Swiffers and Swiffer pads, and they'll like go clean the floor, and they'll also like, clean their device wheels. And I think that's a very good habit to get into, and good thing to do at tournaments. One last thing I just wanted to talk about, learning from your failures. So things are going to happen. You're gonna run into problems as you go through the season, and the most important thing to do is to make sure that you prevent it from happening again. Especially if you're preparing for nationals and that's your end goal. You want to make sure any issues that happen at invitationals or regionals or when you're practicing, that you don't just write it off as, oh, that'll never happen again. That was just a freak accident. Because more than likely it could happen again, and you do not want that. So to the left, you can kind of see we had a problem with our rotary encoder. We didn't have a good connection between the belt and the front axle, and the thing it wasn't counting the rotations properly, and it just flew into a wall and destroyed itself. And this was like a few days before an invitational, I believe, and we just had to reprint the entire piece and then scramble to get everything working again. So and something if there we did have a couple things that we improved. We made sure the encoder was having better contact. We made sure to check that very often to make sure that belt wasn't slipping. I believe we also glued a few of those parts in place with epoxy, and we reprinted that front piece to be a bit more sturdy, have more contact. I think we filleted a couple parts so we smoothed the corners, because having a 90-degree angle corner is not very strong compared to if you just had a fillet where it was smooth. So there's a couple things that we did to improve that. And then below with this video, let's see if I can get this to play. So we had a problem with the with our code, and it didn't the part of the code where it starts to go towards the target point doesn't kick in until after the encoder realizes it's gone a certain amount. I think this was 8.5 meters it was supposed to go before it would kick in. And the vehicle just would always go past 8.5 meters. We never just had that problem until, of course, competition, where somehow the first part of the code just didn't make it all the way there. I think the battery wasn't charged properly. That was definitely an issue. And so the vehicle kind of just stopped at the 8-meter mark there. And it didn't pass the timing mark. So the code wouldn't kick in to continue the run. It wouldn't continue to approach the target because it hadn't gotten through the first part of that program. So from there on, we always implemented a backup code system where if it realized, oh, I haven't gotten past that 8.5-meter mark, I need to give it a couple extra pushes, and the motor would flip on and just get past the 8.5-meter mark, and then it would proceed into the target approaching part of the code, which is like a big system of loops that we used. And so I think with that covers everything that I wanted to talk about. If you have any questions, please feel free to comment below, or you can send me an email. I'll try to be responsive about this, and I hope this was helpful.